Welcome back. Now we are going to discuss some important questions. I cannot say important questions. The difficulty in chemistry is each and every sentence in the text can be converted to a question. Not a question, two questions, one direct and one indirect. So, we cannot say which is important, which is not important. So many questions are there. Out of that, very few questions I am going to discuss now. Okay. And I told you we can convert each and every sentence to two questions, one direct and one indirect. For example, define Schottky defect. Like that we can ask one question. Instead of asking like that, another question we can ask from the same topic is, they can give a diagram like this. Either they can say define Schottky defect, okay, or instead of asking define Schottky defect, a diagram will be given to you like this. Diagram like this will be given to you, one positive, one negative. A picture they will give and they will ask, this diagram represents what type of point defect? Question number 1. Give an example of an ionic solid showing this defect. Question number 2. 3. What happens to the density of the solid because of this defect? Like that 3-4 questions they will ask with half mark. Okay. So, directly and as well as indirectly we can ask questions. Now, let us see some important questions. Okay, look at the monitor. The first question, what is the total number of atoms per unit cell in a face-centered cubic structure? You know, calculation is very simple. Previous class I was explaining all this. Instead of asking face-centered cubic unit structure, they can ask BCC and also they can ask simple cubic. What is the total number of atoms per unit cell in a face-centered cubic structure? FCC unit cell means atoms occupy at the corners as well as at the centers of the faces. Corner contribution as already I taught, 1 by 8 into 8, that is equal to 1, and face center contribution is equal to 1 by how many face center contribution? 1 by 2 into how many faces are there? 6 faces are there. So, you can calculate like that. Similarly, in a body centered is equal to 3. So, total number is equal to 4. In a BCC unit cell, if it comes, the calculation already I told, it can come like that, or in a simple cubic also it can come like that. Next question, what type of substance exhibit antiferromagnetism? Today, now only we did that, what type of substance exhibit antiferromagnetism. Antiferromagnetism is exhibited by substances in which magnetic dipoles are aligned in such a way that magnetic dipoles are aligned in a compensatory way, so that the net magnetic moment is equal to 0. Then the next question I wanted to show you is, see that problem, niobium crystallizes in a body centered cubic structure. If its density is 8.55 grams per centimeter cube, calculate the atomic radius of niobium. Niobium crystallizes in a body centered cubic structure. If its density is 8.55 grams per centimeter cube, calculate the atomic radius of niobium. This type of problems, we have the formula D is equal to Z into M Na A cube. Density of a solid can be calculated by using this formula, where Z is the number of atoms, M is the atomic mass, Na is the Avogadro number, A is the edge length of the unit cell. Here what is missing in this? When you write down all the steps, you can see it's a BCC unit cell, so Z is equal to 2. Then density is given there, Avogadro number will be given there. Then what is missing? Atomic mass will be given there. A you have to find out. By using this formula, A you have to find out. Then after that, how to calculate the radius, of an atom. In this type of problems, to find out the radius of an atom, what you have to calculate from the given formula is A. Then by using this A, you have to calculate the radius of the atom. How to calculate the radius of the atom? Now I will tell you some relationship. In an FCC unit cell, 4r is equal to root 2a, where r is the radius of the atom. In a BCC unit cell, 4r is equal to root 3a, where r is the radius of the atom and a is the edge length. In a simple cubic or a primitive unit cell, 2r is equal to a. So by using these relationship we can calculate the radius if you find out a, that is the edge length. So for FCC use this relationship, for BCC use this relationship, and for a simple cubic structure use this relationship. Okay. So that is the method of calculating this type of problems. Now what we are going to see next is, okay, see the problem. An element has a body centered cubic unit cell with a cell edge of 286.65 picometer. Density of the element is given there. Use this information to calculate the number of atoms in 208 grams of the element. Again, we have to use the same formula, D is equal to Z into M, Na into A cube. When you write down all the steps, you can see everything given there. Z is equal to 2 for BCC unit cell, that we have to by heart already. For FCC unit cell, Z is equal to 4, and for simple cubic, Z is equal to 1. We know all these data except what? M we do not know. Substitute everything, calculate M, that is the atomic mass of the solid. Okay, calculate atomic mass of the solid for this particular problem. Then what is the question actually? The question is not calculating the atomic mass, they are asking how many atoms are present in 208 grams of the element. We know the relationship 1 mole, that is atomic mass, 1 gram atom, 1 mole of a substance contain 6.023 into 10 raised to 23 atoms. So you calculate M, say the value of M is equal to, suppose we calculated M is equal to 50, we are getting grams per mole, we are getting this as the answer. Now we know that 50 grams per mole contains 6.023 into 10 raised to 23 atoms. These are the number of atoms present in 50 grams. This is the given, remember this is the atomic mass. And how much mass they have given? 208 grams, therefore contains how many atoms? This is what we have to calculate. So calculate X, that X will be equal to the number of atoms present in 208 grams of this element, that is 208 into 6.023 into 10 raised to 23 divided by 50 will be the answer. Okay. Now let us see the next question. Yes, see the question. So many questions I have written over here, but I am reading out only very few questions. See the third bullet over there. Calculate the packing efficiency of a metal crystal for a simple cubic lattice, or they can ask BCC lattice or FCC lattice. Calculate the packing efficiency. Now what is packing efficiency? What do you mean by packing efficiency? That is the fraction of the volume occupied by the atoms. That we can calculate the packing efficiency, we can calculate by using the formula volume occupied by atoms in a unit cell, into 100 divided by total volume of the unit cell, This is the formula for finding out packing efficiency. Derivations you have, you can by heart the derivation, and directly it is a textbook question only, directly we can substitute all these things and we can calculate the packing efficiency. Okay. For BCC you will get the answer 68%, for FCC you will get it as 74%, and for simple cubic you will get it as 52.4%. Again direct question it is. Okay, now again see that third problem over there. An element with molar mass, they have given a molar mass, forms a cubic unit cell. What type of cubic unit cell, that is not mentioned there. Edge length, cell edge, that is written there, that is A is there. A is written, molar mass is written, density is also given. What is the nature of the cubic unit cell? So they are asking nature of the cubic unit cell. Okay. So molar mass is there, Avogadro number will be there, cell edge will be there, density will be there. So only what is missing there in that question? Type of the unit cell they are asking. So Z is missing over there, and you have to calculate what? You have to calculate Z. If you are getting Z is equal to the same formula we have to use, D is equal to Z into M divided by Na into A cube we have to use. When you calculate Z, and if you are getting Z is equal to 1, then you will say it is simple cubic, and if Z is equal to 2, you will say it is BCC, and if Z is equal to 4, then you will say that type of the unit cell is equal to FCC. Now let us see another question. Explain, see the question, look at the question. Explain how much portion of an atom is located at corner and body center of a unit cell. Corner contribution, I was explaining with lemon and all, 1 by 8 into 8. So corner, how much it is there? 1 by 8. Then body center, inside the body, that particular atom is not shared. So body center, it is fully, it belongs to that particular unit cell. So corner it is 1 by 8 and body center it belongs to that. Okay, see the next question. That is another type. All these questions are based on the different theory concepts. A compound forms hexagonal close packed structure. What is the total number of voids in 0.5 mole of it? How many of these are tetrahedral voids? When we studied voids, there is an important relationship in this voids. Number of voids formed, suppose n number of spheres are forming the crystal lattice. N number of spheres form the crystal lattice. The number of voids formed are octahedral voids. Octahedral voids will be equal to n and tetrahedral voids will be equal to 2n. If n number of atoms are forming the lattice, there are n number of octahedral voids in the crystal and 2n number of tetrahedral voids in the crystal. Okay. If n number of atoms are forming the crystal lattice, octahedral voids is equal to n, tetrahedral voids is equal to 2n. This problem is based on that. Once again, see the question. A compound forms hexagonal close packed structure. We don't know how many atoms are forming the hexagonal close packed structure. Let us consider it as n. N number of atoms are forming the hexagonal close packed structure. Sorry, 1 second. What is the total number of voids in 0.5 mole of it? So if there are n number of atoms forming the space lattice, octahedral voids will be n and tetrahedral voids will be 2n. Here how many atoms are forming the HCP structure? 0.5 mole. We know that 0.5 mole is 0.5 into 6.023 into 10 raised to 23. So number of atoms forming the lattice is equal to 0.5 into 6.023 into 10 raised to 23. Then how many octahedral voids will be there? Same. So number of octahedral voids will be equal to 0.5 into 6.023 into 10 raised to 23. How many tetrahedral voids are there? 2n is the relation. So 2 into 0.5 into 6.023 into 10 raised to 23. So this much octahedral void and this much tetrahedral void. So total number of voids will be equal to what? This octahedral voids plus this many number of tetrahedral voids. Okay. So that is the total number of void. How many of these are tetrahedral voids? Answer is there, that is 2 into 0.5 into 6.023 into 10 raised to 23. Now let us see the next question. Yes, another question based on today's topic. Analysis shows that nickel oxide has the formula Ni0.980. What fraction of the nickel exists as Ni2 plus and Na3 plus ion? Okay, see the question carefully. Analysis shows that Ni0.980 is the formula of nickel oxide. That means a particular type of defect is there, that Ni in Ni0.98 exists as Ni2 plus and Ni3 plus. Okay. Now let us see, this problem you have to solve based on the principle that the total charge of an ionic crystal will be equal to 0. The total charge means charge of the cation plus the charge of the anion will be equal to 0. Now let us see what is the, how we can solve this problem. So 0.98 Ni, that means both Ni2 plus and Ni3 plus. Both Ni2 plus and Na3 plus together only 0.98. Now let us take, let Ni2 plus is equal to x. Just consider Ni2 plus is equal to x. So Ni3 plus will be equal to what? 0.98 minus x. So consider 0.98 is a combination of Ni2 plus and Na3 plus. Out of that Na2 plus we just consider it as equal to x and Na3 plus 0.98 minus x. Now what is the total charge of this particular solid? That is equal to 0. That is what is the concept behind this. So, we are going to calculate that like this. What is the charge of Na? 2 plus is the charge. So, 2 into x plus, what is the charge of Na? 3 plus is the charge. So, 3 into 0.98 minus x plus, what is the charge of O? Charge of O is minus 2. So, minus 2 into how many O are there? 1. So, total charge is equal to 0. So, write down like this. The total charge of the ionic solid is equal to 0. Already it is written here. Now, simplify this and find out what is x is equal to. Find out x from this. So, that x is equal to what? Na2 plus, the number of Na2 plus we calculated as x. I think the answer we are getting is 0.94. Then we have to go for the calculation. What fraction of nickel exists as Na2 plus? In order to calculate what fraction, what we have to do, the total is 0.98. So, the percentage of Na2 plus, percentage fraction of Na2 plus is equal to 0.94 divided by 0.98 into 100. I think you are getting the answer 96% Na2 plus, then Na3 plus directly we can subtract from 100 and you will get it as 4%. I think all of you understood the problem. Okay, it is a different type of problem purely based on the theory. Now, let us see another problem again based on theory. See that question. If NaCl is doped with 10 raised to minus 3 mole percent SrCl2, what is the concentration of cation vacancies? This problem is directly from that impurity defect. When a monovalent cation is replaced by a divalent cation in the lattice site, the number of cation vacancies will be equal to the number of divalent cations present in the site. That is what is the theory we have to learn. Okay, the number of cation vacancies will be equal to the number of divalent cations in the site. So, NaCl is doped with SrCl2. So, what comes there instead of 1 Na plus, what will be over there? 1 Sr2 plus will be there. If 1 Sr2 plus is there in the site, how many cation vacancy will be there? 1 cation vacancy will be there. If 2 Sr2 plus are there in the site, how many cation vacancy will be there? 2 cation vacancy will be there. If 3 Sr2 plus are there in the site, how many cation vacancy will be there? 3 will be there. Like that, how many, what is there in the question? 10 raised to minus 3 mole percentage of Sr2 plus ions are there in the site. That means percentage, so cation vacancy equal to what? Number of Sr2 plus ions, that is equal to what? 10 raised to minus 3 mole percentage. That is equal to 10 raised to minus 3 into 6.023 into 10 raised to 23. All so many times 6.023 into 10 raised to 23 is coming, because we know that 1 mole is equal to 6.023 into 10 raised to 23, whatever it is. Okay, divide. So, this much, this is the number of that what? Number of Sr2 plus, this much number percentage is there. So, in order to convert that, what we have to do? 10 raised to minus 3 into 6.023 into 10 raised to 23 by 100. So, this is the answer. This many Sr2 plus ions are there. That means what? This many cation vacancies are also there. Again, so many questions are there. Okay, why does table salt NaCl sometimes appears yellow in color? Today we did, that is due to the presence of what? F center. Why does window glass of old buildings look milky? Why? Due to the slow heating, what happens? Glass is an amorphous solid, it undergoes slow crystallization, that is why it looks milky, not due to the presence of calcium carbonate or something else. That is a mistake always children used to make. Why is the window of glass of old buildings thick at the bottom? Okay, reason, glass is a pseudo solid, it is a supercooled liquid, it can slowly move towards the bottom. Okay, that is the reason. Like that, many questions are there, direct as well as indirect. Now, today's time is almost over, so I am going to wind up. One thing I wanted to tell you is, you have to, your studies, how you are studying your chemistry, always you have to practice. Practice is the most important thing you need. Now, the 12th standard result has come. Many are getting very good marks. Those who got very good mark, they strived for that. That's why they got that mark. Like that, you all prepare well. The 2 months vacation you have to utilize and study hard. Okay. Thank you.